All right, we are back and better than ever. This is part 2 of our discussion on the standard normal distribution. And we left off, we had just finished example B. Now we're going to do example C. And it's just a little bit more involved. So we are finding the probability that the standard normal variable C lies between negative 0.41 and 0.67. Okay, so what are we looking for here? Well, I think you'll agree if I could take all of this area here, all of that area here, so that would be the probability that z is less than or equal to 0.67. So just keep that in your head. And I could subtract out this little piece here. I'd be left with the yellow. Okay. Remember, this table calculates the area to the left of the curve. So what I want to do is take the probability that z is less than or equal to 0.67 and subtract the probability that z is less than or equal to negative 0.41. Okay, so let's do that. So 0.67, so this one, and here we go. Looks like it's going to be right there. So this is 0.7486. So this is going to equal 0.7486 minus probability that z is less than or equal to negative 0.41. So I go here. Oh, hold the phone, Chuck. These are positive numbers. How in the world am I going to be able to use my table for a negative value? Because these are all positive. Very simple. We are going to use symmetry. It just takes a little bit of thought. And I'm going to show you what I mean here using two curves. Okay. Maybe I'll just need one. We'll see. Okay, so here's our mean, and our mean is 0. Here's our mean, and our mean is 0. This is a standard normal distribution. Okay. Well, we don't have negative 0.41, but we do have positive 0.41. So here's 0.41. And I think you will agree that negative 0.41 is the same distance from the mean as positive 0.41. In fact, it's 0.41 away from the mean. Okay, so by symmetry, this area here has to be equal to this area here, right? Okay, so all I have to do is calculate this area right here. So let's say I have 0.41. How do I do that? How do I calculate this area right here? Because this table gives area to the left of the piece of data. Well, remember, I just take 1 minus the probability that it's less than 0.41. Okay, because if I take, remember, the area under the curve is equal to 1. So if I take 1 minus this here, I get this, which is equal to this. Okay, so minus 1 minus the probability that z is less than or equal to positive 0.41. So a quick way to remember that is if I ever have a negative that I have to find the probability of, it's just 1 minus the probability of the positive. Okay, so this turns out to be 0.7486 minus 1 minus probability that z is less than or equal to 0.41. Here's 0.4. Here's 0.01 to make the 0.41. There we go. There we go. Bazinga. 1 minus 0. What is that? 6591. Now this would be on a paper 1, so you'd have to do all of this by hand. I'm not going to show you how to subtract a decimal. I will just tell you that the answer is approximately 0.4 0.08. Okay. All right, so that is that. Let us move on. Okay, now we're getting to interpreting z values. We're actually going to calculate our own z values. If x is an observation from a normal distribution with mean mu and standard deviation sigma, the z-score of x is the number of standard deviations x is from the mean. So the z-score is actually the number of standard deviations. So if I have a piece of data where its z-score is 1.84, then it's 1.84 standard deviations to the right of the mean. If it's negative 0.273, then that particular piece of data is 0.273 standard deviations to the left of the mean. Okay, so that makes it very simple to compare pieces of different data. And this is the example I gave at the beginning of this section. We got a girl here who scored a 73% in history, and the class mean was 68, and the standard deviation was 10.2. All of these are percents. In math, she scored a 66, the mean was a 62, standard deviation is 6.8. And now, clearly, I mean, she had a better grade in history than she did in math, but how did she perform compared with the rest of her class in those two subjects? That's why we need to be able to standardize our scores. Okay, so in order to do that, all we have to do is find the z-score. Okay, so let's do that. So let's do it for, here, I've got room up here. So let's do it for history. Okay, so for history, z, and since it's all in percents, I'm just going to drop the percent. Z is going to be the piece of data, 73, minus the mean, which was 68, divided by the standard deviation, which is 10.2. And I will tell you that that is about equal to 0.490. Okay, then for math, okay, z-score equals her actual score in math, 66, minus the mean, which was 62, divided by the standard deviation, which was 6.8, and that is approximately equal to 0.588. Okay, so in which class did she do better than her compared to her peers? This is 0.588 standard deviations above the mean, and her result in history was 0.490 standard deviations above the mean. So her result in mathematics was better because she was further away. She was further above the average score in math than she was in history. So she performed better as compared to her peers in math, even though she got a better score in history. Will that always be the case? Well, no, but of course we're going to give you an example where the lower score is better compared to your peers, to the peers, just so you can see that that possibility exists. Okay, just one more video on this topic should wrap it up. I'm going to stop, take pause, and we will be right back.